Cryptographic systems fundamentally rely on randomness. From RSA key generation to session tokens and nonces, randomness underpins the unpredictability that secures digital communication. However, not all randomness is equal. The strength of cryptographic operations hinges not just on algorithmic complexity, but on the entropy, the actual unpredictability of the random numbers generated. When entropy is insufficient, even a theoretically strong algorithm becomes trivially breakable. Entropy refers to the amount of uncertainty or randomness present in a system. In cryptography, high entropy sources ensure that keys or tokens are unpredictable, even to an attacker with partial knowledge of the system. A perfect example of entropy failure is the Debian OpenSSL incident from 2006 to 2008, where a patch to the OpenSSL library drastically reduced the entropy of the key generation process. As a result, only 32,767 possible keys were generated on many systems, allowing attackers to perform bulk GCD computations and recover thousands of private RSA keys with ease. Another well-known case is the Android SecureRandom vulnerability in early versions of Android 4.x, where poorly seeded random number generators led to the compromise of Bitcoin wallets. Attackers could reconstruct private keys because the same or predictable entropy was used repeatedly. This illustrates that even in systems with strong encryption libraries, flawed entropy sourcing can completely undermine security. In most systems, random numbers are generated using pseudorandom number generators, or PRNGs, which are deterministic algorithms seeded with an initial source of entropy. While PRNGs can produce statistically random output, their security entirely depends on the unpredictability of the seed. If the seed is too short, reused, or drawn from predictable sources like timestamps or process IDs, an attacker can reverse engineer the output stream. Hardware-based entropy sources are becoming increasingly important. Modern CPUs often include hardware random number generators, such as Intel's RDRAND or ARM's True Random Number Generator, that collect entropy from physical phenomena like thermal noise or quantum fluctuations. These are useful, but even hardware solutions must be audited. Some early implementations were discovered to produce biased or predictable outputs under specific conditions. Security architects must also address the boot time entropy problem. When a system starts up, it may not have had time to gather sufficient entropy from user input, disk activity, or network noise. If cryptographic operations like SSH key generation or TLS handshake occur too early, they may use low entropy values, opening a vulnerability window. Proper solutions include entropy caching, HSM-assisted boot, or reseeding mechanisms. Ultimately, entropy is the invisible cornerstone of cryptographic security. Developers and system administrators must treat entropy sources as critical infrastructure. This means using OS-provided secure PRNG APIs like dev random, dev urandom, or geetrandom, avoiding custom RNG implementations, and periodically testing entropy health. Without robust entropy, even 2048-bit keys or advanced algorithms can be defeated by attackers wielding nothing more than statistical tools and patience.